Morning. We are going to finish up chapter 7 on photosynthesis. What we've talked about so far is what is happening to the water molecule when we take an electron from that water molecule and excite that electron using electromagnetic radiation in the form of light to produce oxygen as a byproduct. So that's kind of the photo part of photosynthesis. And now we're going to focus for the remainder of our time on how do we actually make something like a carbohydrate such as glucose by using inorganic carbon as our starting material. So what we've previously focused on is, again, the light-dependent reactions which are taking place inside of the chloroplast, specifically within the thylakoids. And what we have already covered is how we are able to utilize light energy to make ATP, NADPH, as well as oxygen. And this happened in several stages, utilizing photosystem 2, and then a subsequent reactivation of that electron with photosystem 1. What we'll focus on now are our light-independent reactions, also called the Calvin cycle, in which we will be synthesizing carbohydrates. As opposed to in the thylakoids, these are actually occurring in the stroma, but we're still inside of the chloroplast. And in order to build something up, in order to take carbon, just inorganic carbon, such as CO2, and make something like glucose, that's going to take a lot of energy. We're going to get that energy from ATP, and we're going to get the electrons that we're going to put into this molecule, we're going to get that from NADPH. This is going to take place in 3 key steps. The first is known as carbon fixation. The second is carbon reduction, in which we will actually be making the carbohydrates. And then the third step is regeneration, and this is going to be regeneration of our starting material, which is ribulose bisphosphate. So if we're looking at the overall stoichiometry of the Calvin cycle itself, what we're going to be doing is taking 6 CO2 molecules and converting that into 3 carbon molecules, which is known as glyceraldehyde 3-phosphate. So 2 glyceraldehyde 3-phosphates would be necessary to make 1 glucose molecule. As you can see, this is going to take a lot of energy, and that's going to come in the form of ATP. And we also are going to be getting our electrons from NADPH. It's important to note here that we are going to be utilizing more ATP than NADPH, and the thylakoids are able to compensate for those needs as we already previously described. So again, those 2 glyceraldehyde 3-phosphate molecules, those are going to be 2 3-carbon molecules, and they're going to be the precursors necessary to make things like glucose, sucrose, starches, cellulose, etc. All right, and just to remind you once again, we've already talked our way through all the light reactions that were happening in the thylakoids, but now all these reactions are taking place in the stroma. All right, so as I already mentioned, there's going to be 3 phases to this Calvin cycle. The first is going to be fixing carbon dioxide. The second is going to be causing the reduction of that molecule. So again, reduction is gaining electrons. And then we're going to be producing our carbohydrates. And then we're going to have to regenerate our starting material, which is ribulose bisphosphate. So let's start off discussing carbon fixation. So in order to make 1 glucose molecule, which is C6H12O6, it makes sense that we're going to require 6 CO2 molecules in order to do that. In order for this whole reaction to be balanced and in the end to regenerate our starting material, which is this ribulose bisphosphate, because this entire thing is a cycle, we're going to start with 6 CO2 molecules, 6 molecules of the ribulose bisphosphate, and we're going to generate 12 3-carbon molecules known as phosphoglycerate. Now this might seem a little overwhelming at first, but go through this a couple of times and it'll start to make sense. So let me show you the main thing I want you to be able to do is to track your carbons. So if we're starting with 6 CO2 molecules, again, that is just 6 carbons. The ribulose bisphosphate, so a ribose sugar, we've already talked about different types of sugars in the past. That's a 5-carbon sugar, so if we have 6 of those, that would mean we have 30 carbons. So we're going to have the 6 carbons from CO2 plus the 30 carbons from the ribulose bisphosphate. So that's 36 carbons altogether. So in order to balance that, if we have 36 carbons to play with, and we are generating a 3-carbon molecule, so we just take 36 divided by 3, and that is going to leave us with 12 3-carbon molecules that we just generated. So it is all balanced. The enzyme that is catalyzing this very important reaction is known as Rubisco, and is one of the most abundant enzymes in the entire planet. All right, so we are saying carbon fixation. What exactly does that mean? Well, we have, again, our 5-carbon sugar, which is that ribulose bisphosphate. So 1, 2, 3, 4, 5. Bisphosphate just implies that we've got 2 phosphate molecules. So you can see that 1 and 2. And we're going to take our CO2 molecule and attach that onto this 5-carbon molecule. And so that is what is depicted here. This is what the Rubisco is going to be able to do for us. So this CO2 gets incorporated, and then we're going to break this now current 6-carbon molecule into 2 3-carbon molecules, which is our phosphoglycerate. And your textbook is going to refer to this as 3-PG. So I just did not want you to get confused about that. So again, if we're going to make 1 glucose molecule, C6H12O6, how many CO2 molecules do you think we're going to ultimately need to fix? Hopefully you came up with 6. All right, so what we've done so far is we've fixed that carbon. We had our 6 CO2 molecules. We attached those onto 6 different ribulose bisphosphates, and then that 6-carbon molecule got cleaved, and so then we ended up with 12 3-carbon molecules. These 3-carbon molecules, the phosphoglycerate, is just going to get rearranged, and we're going to be able to also add some hydrogens onto this molecule, and taking those electrons from NADPH, which we made earlier in the thylakoids, and now we're going to be able to make glyceraldehyde 3-phosphate. And at this point we haven't lost any carbons. We had 12 3-carbon molecules here. We again still have 12 3-carbon molecules. And what does that specifically look like? So here you can see we've got that phosphoglycerate, phosphoglycerate, I should say, and here we've got glyceraldehyde 3-phosphate. So if you look specifically at the molecule, what is different between this molecule and this molecule, you'll notice that the main change is taking place here at this particular carbon. When the carbon is a part of the molecule here, those oxygens are really dominating the electrons, and so carbon here is kind of electron poor, whereas as a part of the glyceraldehyde 3-phosphate, the carbon here is able to really garner the electrons. So again, what we've done is we have made glyceraldehyde 3-phosphate, which is going to require an input of ATP and NADPH, which was already synthesized earlier in the light reactions. And in order to make 1 glucose molecule, 1 6-carbon molecule, it makes sense that we're going to require 2 of these glyceraldehyde 3-phosphates to come together, 2 3-carbon molecules, to make a 6-carbon molecule. So if we are pulling out 2 of these 3-carbon molecules here, that's going to leave us with 10 glyceraldehyde 3-phosphates to be recycled back in order to form our starting material, the ribulose bisphosphate. So if we took out of the 12, so here we had 36 carbons. We took out 2 of those. That leaves us with 30 carbons. So 12 times 3 is 36. Minus the 6 carbons is going to be 30 carbons. And if you are generating a 5-carbon molecule, 30 divided by 5 is going to be 6. And so we'll be able to regenerate our remaining starting material, the ribulose bisphosphate. And again, this is going to take some additional ATP. So here this required 12 ATP and 12 NADH. And now this is going to require 6 additional ATP. And that's why, again, we need more ATP for this reaction than NADPH. So as you can see here, we're going to be regenerating our RUBP so that this cycle, the Calvin cycle, can continue to take place. So hopefully this is beginning to make sense. The synthesis part of our photosynthesis, in which we are going to be making a glucose molecule by fixing 6 CO2 molecules through this incredible cycle. I have also posted on Canvas several additional videos on this topic if you're feeling overwhelmed and confused, and feel free as always to email me with your questions, and I'm happy to answer those offline.